In this final video lecture, we will be discussing section 7.2, transformation of initial value problems. This section is going to focus on the concepts that we learned in section 7.1 regarding Laplace transforms and their inverses and how they relate to solving initial value problems of differential equations. Before we get started, we need to get a couple of definitions out of the way. The first one is regarding functions being piecewise smooth. And to be honest, this definition is what you think it would mean. So a function is piecewise smooth on a bounded interval if it is piecewise continuous, meaning you can cut it up into finitely many intervals, all of which are continuous, and differentiable except at finitely many points, namely at the endpoints, with the first derivative also being piecewise continuous. So you can think of this exactly as you can separate this function into finitely many intervals, each of which are smooth, meaning no sharp cusps, no discontinuities, anything of that nature. And so theorem 7.2.1 is going to require that condition. Suppose that a function f of t is continuous and piecewise smooth for all t less than or equal to 0, and it's of exponential order. And so we just remind ourselves what that means. We introduce exponential order in 7.1. It means that there exist non-negative integers mc and capital T such that the exponential function me to the ct bounds above the absolute value of our function f of t. If all of these conditions hold, we're continuous, piecewise smooth, and of exponential order, then we can define the Laplace transform of the derivative. And more specifically, what it is s times the Laplace transform of the original function minus the initial condition. And then, of course, making use of the capital F notation, that just is another way to write the Laplace transform of f of t. So the takeaway here is that this theorem is giving us a way to express the Laplace transform of a derivative of a function. This is useful, but we might want to take derivatives of higher order or Laplace transforms of higher order derivatives. And so the corollary does exactly that. So suppose f and all of its foreseeable derivatives are continuous and piecewise smooth and all are of exponential order. Then what we have here is an expression for the Laplace transform of the nth derivative of the function. And so what you'll notice is it's taking into account an initial condition on f, but also on the first derivative all the way out to the n minus first derivative. So we're using these initial conditions built into the Laplace transforms of the derivative functions. All right, so this next flowchart is going to lay out how we're going to use Laplace transforms to solve initial value problems in differential equations. So we're going to start up here in the top left with the differential equation. We're going to apply the Laplace operator or the Laplace transform. And what that's going to do is that's going to bring us to an algebraic equation in x of s. So remember, x of s is just another notation for the Laplace transform of little x of t. So when we apply this corollary up here, we're going to get several of those in here. So here's one, for example. So now an algebraic equation. From here, we're going to solve algebraically, and we're literally talking about college algebra, solving for an unknown. From here, then, we're going to find our solution of this algebraic equation, and then we want to undo the Laplace transform by applying the inverse transform. Your result in here is the solution of the dE, and again, this includes the use of the initial conditions. There is no additional step of solving for constants like we're used to doing because of this corollary up top takes into account those initial conditions. So before we jump into an example, I just want to recall the table of Laplace transforms. We will always be referring back to this, both when we're taking transforms of functions as well as inverse transforms of functions. So we'll refer to this frequently. All right, so for number 2, we want to solve the IVP. And so we have this fairly simple looking differential equation. Now this is homogeneous, so we could very easily solve this directly, but we would like to utilize the method here of inverse transforms. So what I want to do is I want to take this differential equation and I would like to apply the Laplace transform to it. Now, we discussed some properties of the Laplace transform, and some of those properties included the fact that it distributes across sums and differences, and also that constants can pull out front. So we could write this as the Laplace transform of x double prime plus 9 times the Laplace transform of x. Now, note that this right here, we don't know what this function is, but what we're doing is we're going to write the Laplace transform as x of s. So these two things are actually equal. So this is the only item that we still need to compute. And so in order to do that, we're going to refer back to the corollary. So this is just kind of like some side work here. Let's determine what the Laplace transform, of x double prime of t is. So let's look back up here. And the corollary says the following. Okay, in particular, we care about n equals 2. So we're going to have s squared times, well, maybe write it down here, f of s. And then this is going to become s to the first, f of 0. And then this will go to 1, and we just get f prime at 0. So keeping this in mind, let's copy this over. So we get s squared and then we're going to get x of s minus s to the first power. And then we want our initial function evaluated at 0, which is 3. And then minus 1, because it's s to the 0, times our next initial condition. All right, so if we clean this up, it looks like s squared x of s minus 3s minus 4. All right, so now we know how to transform this entire differential equation. I am going to take this dE. I am going to apply the Laplace transform, and it becomes s squared x of s minus 3s minus 4, and then tack on what we discussed up here. So we have plus 9 x of s, and then of course on the other side we have equals 0. The Laplace transform of 0 is 0. We now see an algebraic equation in x of s. We would like to solve for x of s. All right, so isolating x of s, we have s squared x of s plus 9 x of s equals, I'm going to move these two terms over, so 3s plus 4. I can then, of course, factor out an x of s. And finally, solving algebraically, we have x of s equals 3s plus 4 over s squared plus 9. So let's pause for a moment and reflect on where we are in the flow chart. So if we refer back to the flow chart, we have applied the Laplace operator. We obtained an algebraic equation in x of s. We have solved algebraically, and we now have x of s equals a solution. All right, so now since we had already applied the Laplace transform here, we would like to undo it with the inverse transform. So we are right here in this flow chart. So we have x of s equals 3s plus 4 over s squared plus 9. The question is, what does little x of t equal? So to undo the capital X of S, we do the inverse transform. And so now is where we want to refer back to our table of common Laplace transforms. So what I'm seeing on the denominator is this S squared plus 9 that looks of the form S squared plus 3 squared, or S squared plus K squared. So we're familiar with this. Let's move back up here. And so we're looking at either a cosine or a sine function, right? So depending on whether we have an S on top or a constant on top. So we look back down at where we're at, and as it turns out, we essentially have both of those on top. So what we'd like to do is we'd like to separate this into two separate fractions. So let's do X of S equals 3 times S over S squared plus 9 plus 4 times 1 over S squared plus 9. This first piece here, we're in good shape because that is precisely cosine of KT for K equals 3. For the other piece, we need our constant K on top. Our K in this case is 3, so I'm just going to rig it up by multiplying by a 3 over 3, and then I want to capture this with the 3 on top with the S squared plus 9 on bottom. So at this point, I am now capable of applying the inverse transform, and I obtain X of S equals, we had discussed that this first expression is 3 times cosine of 3t, and then making sure to keep this 4/3 as a coefficient out front, I have sine of 3t. And that is our final answer. We are not coming up with a general solution first. Rather, this process is streamlined straight to the particular solution with the coefficients already solved for. It's really pretty slick, guys. It's really slick. Let's look at another example here. So I'll bring this down in case you're still copying a little bit. So we have this differential equation. This is an example of a non-homogeneous DE, so would take a little bit more effort to solve if we were solving it directly. Notice here that my initial conditions are going to zero out. So that's going to really simplify things when I find the Laplace transform of the second derivative. All right, so let's give it a go. I want to compute the Laplace transform of x double prime plus 4x first. And so using linearity and the constant multiple rule, I get the Laplace transform of x double prime of t plus 4 times the Laplace transform of x of t. Again, all of this is just represented by capital X of S, so we don't need to do any work there. We do, however, need to flush out the transform of the second derivative. And so that's using that corollary yet again. So if we go back to that, so we have S squared X of S, and then in this case now, all of these initial conditions are going to 0. So what that means is we're not going to get any of those preceding terms. All that's going to live on is the S squared X of S. So let's copy that down. So S squared X of S. And then I'm going to write plus 0 just to remind you that it was because of these initial conditions that we didn't get anything else there. All right, now we must not forget about the right-hand side of the equation. We also need to take the Laplace transform of cosine of t. But we're just going to directly refer to the table for this one. So if we go back up, here's the cosine t function. We get this back out. In this case, our k is 1, so we get s over s squared plus 1. All right, so we have all of the pieces and parts. Let's go ahead and put it all together. So I'm going to start with my differential equation, x double prime plus 4x equals cosine of t. And I'm going to apply the Laplace transform. And that results in s squared x of s plus 4x of s. And this all equals s over s squared plus 1. All right, so now we have an algebraic equation in x of s we need to solve. So I can factor an x of s from the left-hand side, leaving me with s squared plus 4 equals s over s squared plus 1. And so finally, solving for x of s, I have s over s squared plus 4, s squared plus 1. All right, so we've gone down and across our flow chart. Now we need to make it back up. Our goal is to solve for x of t. That is the solution of the differential equation. In order to recover little x of t from capital X of s, we need to take the inverse transform. So now where we're at is we're looking at this expression over here on the right-hand side, and we're like, holy buckets, how are we going to take the inverse transform of this god-awful rational expression? And so the issue here is that we have the product of these two polynomials on bottom. If they were separated, we would be in business because we're probably going to get some kind of a cosine or sine function. But the fact that they're being multiplied is an issue. So what we're going to do is we're going to utilize the method of partial fractions to split this up. So you'll notice that these are both quadratic factors. And using the method of partial fractions, we can split this up as sum as plus b over one of the factors. You pick which one you want it to be. I'll let it be s squared plus 1. And then sum cs plus d over the other quadratic factor. So remember, whenever you have a quadratic factor, your numerator is a times your independent variable plus b, or some linear combination of the two. All right, so now we would like to solve for a, b, c, and d. Once we do that, we will be able to more easily find the inverse transform. So if I multiply both sides through by the common denominator, I am going to get s on the left-hand side, and on the right-hand side, I get as plus b times s squared plus 4 plus cs plus d times s squared plus 1. All right, so here is our expression. At this point, you can now either solve by expanding and equating coefficients, or you can plug in roots of factors. When I teach partial fraction decomposition in Calc 2, we live in the happy world of real numbers. And so at this point, we would say, oh, we don't have any real roots, so we really can't solve. In this class, we've got our big boy pants on, and we're just going to say, look, we can use imaginary numbers. So for example, the root of this factor is I. So I'm going to say if s equals I, then what does this equation become? Well, the left-hand side is I, and then I have an ai plus b times s squared would then become a -1, so this is 3. And then this whole ending term is going to drop out. So now what I have is 3ai plus 3b equals I. Equating the coefficients of the imaginary terms leads to a equals 1/3, and equating the coefficients of the real term leads to b equals 0. So right there, we just solve for a and b. Let's do the same thing for c and d. In this case, we're looking for roots of the quadratic factor s squared plus 4, and so that's going to be 2i. So if s equals 2i, what do we get? We have 2i equals, the whole first term drops out, and then we have 2ci plus d, and then 2i squared is going to be a -4, so we get a -3. So following the exact same procedure here, we have -6ci minus 3d equals 2i. And so our d is going to drop out because we don't have any real terms on the right-hand side, and our c is going to be -1/3. All right, so we have now officially solved for a, b, c, and d. We want to plug it back in up here. And so let me recap. We were working with the transform x of s, and a was 1/3 and b was 0. So I'm going to write this as a 1/3 s over s squared plus 1. And now we have plus. The c was a 1/3, so I have a -1/3 out front, s over s squared plus 4. And now the worst is over. Now we can see that those s over s squared plus 1 and s over s squared plus 4 are an immediate transform to a cosine of kt, where k is varying between 1 and 2. So let's bring that back down. And our conclusion is little x of t equals 1/3 cosine of 1t, if you will, minus 1/3 cosine of 2t. And that's our final answer. All right, so other than the somewhat messy partial fraction decomposition, really as long as you feel comfortable switching in between functions, their transforms, and back again via the inverse transform, this is really a, like I mentioned, a streamlined process to solve initial value problems. All right, we have one more theorem here in this section. And what it's going to do is it's going to give us a relationship between applying the Laplace transform and how it relates to integrals. So our hypotheses here are if f of t is a piecewise continuous function for t greater than or equal to 0, and it's of exponential order, then the following is true. So it says the Laplace transform of the integral from 0 to t of f of tau d tau, notice the taus rather than t's, that is equal to 1 over s times the Laplace transform of the integrand function at t. And then, of course, remember that this Laplace transform notation can be replaced with the capital F of s notation. So what this is saying is you can essentially pay for the integral by dropping the integral and then including this 1 over s, and then just taking the Laplace transform of the integrand. While this is a perfectly fine result, we more often than not are going to utilize this result, the second result, which is an equivalent result, saying that if we want to take the inverse transform of f of s over s, and I want to call your attention to this s factor on bottom, then what we can do is we can drop that s, but pay for it with the integral here inside. And then remember, you're integrating with respect to tau. So then the inverse transform becomes little f of tau d tau. So this seems a little bit clunky, but we'll see where this is actually going to save us a great deal of time in simplifying here in these next examples. All right. So we have just two last examples. Apply theorem 2 to find the inverse Laplace transform of the function. So we are given the transform f of s. We would like to recover little f of t. So we want to take the inverse transform of 3 over s times s plus 5. So what we see here is this factor of s in the denominator. So the previous theorem says we can deal with that s in the denominator and drop it so long as we introduce this integral. So let's do exactly that. This is going to become the integral from 0 to t of the inverse transform of what is now 3 over s plus 5 d tau. So now this function inside the inverse transform looks much more manageable. If we look back up at our table of transforms, we have a 1 over s plus 5 looks very much like this, where a is a negative 5, right? And then the 3 on top is just going to be a coefficient out front. So what we're going to have is a 3e to the negative 5t. So let's copy that back down here. So this is the integral from 0 to t of 3e to the negative 5. And then remember, instead of t, we're using tau here. We don't want to abuse the variable t because it's already in our limits of integration, d tau. So now we can directly integrate this. When I integrate, I'm going to pop out a negative 1/5. So I have minus 3/5 e to the negative 5 tau from 0 to t. So this becomes a negative 3/5 e to the negative 5t, and then minus a negative, or in other words, plus 3/5. And so then here is our final answer for the inverse transform here of 18. So pretty slick that we're able to eliminate that extra factor of s. It allows us to forego the method of partial fractions to splitting this up, essentially, and using calculus in order to do so. So 22 is just another example that's very similar. We want to recover the inverse transform. And we have this undesirable factor of s right here. So let's use that theorem to drop that s. We pay for it with an integral from 0 to t, and we're going to integrate the inverse transform of that same thing, but without the extra factor of s on bottom. And we want to integrate this with respect to tau. Now, I have an s squared minus a k squared. This is where k equals 3. And so if I look back up at my table, s squared minus k squared is one of the hyperbolic trig functions. Now, I don't particularly want to introduce an s on top, but I'm okay with introducing a constant on top. So what I'm missing is a k value there on top to get a sinh popping out. So what is my k value? My k value is 3. So let me do this extra step of adding a 3 on the numerator and the denominator. Oops. So I'm going to write it as 1/3 of 3 over s squared minus 9 d tau. And then we know that constants can pull out front, so that 1/3 is no problem. But now the inverse transform of this is going to pop out a sinh of 3 tau. So I have the integral from 0 to t of 1/3 sinh of 3 tau d tau. And then finally, we need only take the integral of sinh. And so if we did a u substitution, we know that we're going to pop out another 1/3, which is going to result in a 1/9. And then recall the derivative of cosh is sinh, so the integral of sinh is cosh. So I get cosh, or hyperbolic cosine, of 3 tau, and I want to evaluate this from 0 to t. And so what I get is 1/9 cosh of 3t minus cosh of 0 is 1, so minus 1/9. All right, so this concludes our final video lecture of the semester. I hope you enjoyed, and I look forward to seeing you guys in class here on Wednesday.